Hello, everyone. Welcome to the Causality for Artificial Intelligence and Machine Learning lecture, short CAI or CAI, however you want to call it. It's a follow-up to our seminar from last term, which was quite successful. People were asking for a lecture. So here you go. We want to jump right into one of the biggest motivations for why we actually need causality in machine learning. Consider the following example, adapted from the famous book by Jonas Peters et al. In machine learning, we'll encounter data sets like the one on the left. So we see two data sets here. They look quite similar, but they have different features. So on the top, we have activity of a gene A and a phenotype being expressed. And on the lower row, we have the same thing, but just for another gene, for a gene that we call gene B here. Don't worry, you don't need to be an expert in biology or any of that. This is just for illustration purposes. This could be any other features. And now we ask the question, what is the difference between those two data sets with respect to learning? Well, you would guess now that it has something to do with causality, but you would also probably think that, well, these data sets look really similar, so you wouldn't expect any difference. So you're quite curious, I figure. Well, we will ask the following question now. It's a bit out of the ordinary, as it's also, in a sense, out of distribution. What if we kill the activity of the gene? So we are asking now about a data point, essentially, that we haven't observed, or multiple data points for that matter, the ones which have activity of gene A and B respectively being 0. So that's why you see the red line here with a question mark. And so that's essentially a question of generalization. And well, it turns out that causality is the answer for that. So if we were to kill the activity of the genes respectively, then actually the two data sets would reveal a difference, because in the first data set, we have gene A actually being a cause of the phenotype. So if you change the activity of gene A, the phenotype will react to it. And so if we had our regular linear regression line, it would still work. So you can just extend the line essentially, and you would be in this kind of 0 to 4.5-ish range. But for the lower data set, for data set 2, the same thing wouldn't work, because gene B is actually not a cause. There is a common confounder, so a common cause, which is both causing gene B and phenotype. And that's why it seems like, they are causing each other. At least we see this correlation, just like in data set A. But if we were now to obviously kill the activity of gene B, since it's not, causing the phenotype, we shouldn't be changing our prediction. We would still expect the same range of, what it is, 7.5 to 16.5 approximately here. So our prediction with a linear regression line would be completely wrong. And this is all just because, well, we didn't consider the underlying causality. So in conclusion, without considering the causality, the best that our algorithm can do in principle, conceptually, is to say, I don't know. And we really, really, really want to know. But yeah, where this comes from, there's a lot more. And this is, what this lecture is going to be about. Today's lecture, especially because we're talking about motivation and, all these kinds of things. But before that, now let's first introduce ourselves. So the seminar, this lecture, is officially part of the AI/ML syllabus. So it's head by Professor Dr. Christian Kersting, who's also going to be here for the lecture. Today it's us. Eventually he's going to be here. We're taking care for him. Dave is going to hold most of the lecture today. Mate that's me. You've just met me already. And Moritz is also with us here. Before we kick off, just a quick on logistics. So we're going to talk about, participation, communication, grading, and timeline. In this recording, that's not of a matter. So this is a post-recording in this case. So all of these things have happened during the lecture. That's why I also didn't hear Dave or Moritz now. They introduced themselves live during the lecture. So participation, just briefly. So we have over 100 students registered. Most of them are masters. Then it's bachelors. We also have PhD candidates and people from outside of Germany. During the lecture, it was more like 60 people, roughly. but then on the channel afterwards, after we registered, now it's about 80. So all within expectations, I'd say. The lecture might be tough in the sense that, you know, it's really building on a lot of things. So that's why we advise you to self-select. So obviously it's about courses like, you know, the necessary maths, things like statistical machine learning, but also if you had something like probabilistic graphical models, that would be very helpful. But obviously also your experience. Someone who's in their master's, they have very likely completed a bachelor's successfully. At least they should have, conceptually speaking. They're long in the game. They have had, you know, internships and these kind of things. So if you're a bachelor's, don't feel discouraged. By no means, we are happy to have you here. It's just that, you know, you should take care of this yourself. And then again, it can be rewarding at the same time, right? So we really just want it to be easygoing for both of us. For the communication, so there won't be any Toucan or Moodle, but just Mattermost, which is like a blue team Slack, and it's what Christian's lab is using for the daily work communication. So you can really find us there, and we are going to answer. We're going to answer quick, and we have all the nice features of using LaTeX and sharing images and videos and formatting due to Markdown and all these kind of nice little features. The channel name is Kai Lecture Winter Semester 23-24, Causality for AI and ML. And yeah, everything is really shared there. So the slides, the references, this recording, but also your questions or your thoughts, right? So you can always feel free to share impressions or anything related to the topic, right? So of course, there's some kind of formality in here, but we want to keep it more informal in the sense that, you know, everyone feels safe to engage and just share, because this is a place of learning after all. Yeah, also for the recordings, you know, we'll try to keep up. We'll try to make it a quick turnaround. So, you know, people who simply cannot attend, that they also get a chance. But for the people who can attend, please stop by once in a while at least, because it's more fun for us if there are more people in person. This we did. So for anyone who hasn't done this yet, but I think we have everyone covered by now, it's just creating a profile, using your first and last name, using a profile pic, and then letting me know so I can invite you to the channel. For the grading, it's really simple. So we just have a final exam. We've heard from some people that there's, you know, some overlap potentially with something like computer vision. We are currently in the process of figuring this out. But yeah, we have the slot from 11 to 14 p.m. on 20th of March next year in the bigger room, which is above the lecture room. And now, maybe most importantly, for the course structure, the timeline. So we are going to have two parts. The first part is going to be pure causality. So we are really going to learn the basics for discussing all the ideas, which is going to happen next week. Then, you know, foundational ideas for Pearl's formalism, which is the key formalism that we are going to use, arguably the most successful one in AI and machine learning. And then we are also going to have a sneak peek beyond Pearl, things like actual causation in the discussion with Halpern, Granger causality, and so on and so forth. And then in part two, which is going to be the slightly bigger part, we have causality for and with AI and by implication machine learning. So it's all kinds of topics within AI, metrics, explanations, fairness, scaling up, etc. All kinds of things essentially which are downstream oriented topics, which we're going to discuss in the light of causality. A total of 15 dates, and not all of them will be classical lectures. So the main paradigm will be a classical lecture, so you can just enjoy listening, but you know, we encourage you to always engage. But then we are going to have at least one coding tutorial, which is hands-on, and you really get the experience, not just the actual implementations, but just, you know, what it really means to do these things, right? Like learning by doing. And then a kind of reverse classroom thing. You don't necessarily need to prepare anything, but it's just, you know, we are hanging out together and discussing all you've learned up to that point. So today, course logistics that we just essentially are wrapping up now, and then Dave is going to talk about motivation. Then next week we have things like probabilities, independence, graphs, and so on. The week after that, in November, we have Pearl's causal hierarchy. We're going to discuss the theorem and the proof, and essentially the foundational result and of causal inference and all the associated levels of intervention, counterfactuals, and well, association. Discovery of causal structures, which, you know, is causal discovery or causal learning in the most broad sense, arguably. And this could be a whole lecture of its own. But that's the cool thing about this lecture. It's kind of adding to the overall picture that is available online, in that we are not just covering, for example, Pearlian causality or the potential outcomes framework or any niche topic, say in machine learning, but we are really trying to give the bigger picture, but then also have a focus on Pearl and AI and machine learning related topics. But yeah, don't forget, this could be a whole course of its own, just like the fifth date as well, identifying causal effects, which is arguably the next big strand. So the first guys are kind of concerned with, you know, learning from data, the actual causal relationships, but then the other ones are saying, well, it's nice to have the relationships, but what can I do with them, right? So how do I actually identify any causal effects? What does it mean, right? Then on the 6th day, so end of November, we're going to have the code tutorial, and it's going to be on these topics, right? So we're going to talk about the ladder of causation. We're going to talk about discovery and identification. Then in December, we are going to go beyond Pearl and have our first, you know, reverse session. Then mid-December, we have fairness and representation learning. Also, representation learning could be a whole course of itself, right? So by now, maybe even fairness with all the work that's been going on in the literature. But for example, Chandler Squires at MIT, he actually gives a representation learning course. We are also going to share all of these references that we find, that are in general all available there. And honestly, they're all amazing. So, but you're going to hear also from Dave a little on this later on. Then right before Christmas, we're going to slow down a little bit and do another reverse session, which is essentially going to be for all of part 1 and the beginning of part 2, right? So part 1 ends really with session 7, and then part 2 starts. And then in the new year, mid of January, so it's going to be a bit longer break, but then we have the topic like measuring causality or explanations. At the end of January, we're also going to talk about neural models, right? So all the craze about deep learning and how it integrates with causality. And then for essentially the final technical topic, we are going to talk about large scale, which is, you know, figuring out how to go beyond the low dimensional setting in causality and still have causality, and what could it even mean in something like large language models, which has been a hot topic over the last half a year at least. And then our final session is again going to be a reverse classroom, where we are going to just talk about everything we have learned and obviously the exam. And so just as a reminder, briefly, you're going to see the slide at the end as well. So same place, same time next week, 27th of October, in one of the small Piloti rooms, from 1:30 p.m. to 3:10 p.m. And any general questions or thoughts, as I said, or impressions, share them on the Mattermost. And if there's anything of single concern, you can just direct message me. And with that, now it's Dave's turn. So in the lecture, Dave was starting to talk now, because this is a post-edit. I'll just take over, and then we were going to switch to Dave's audio recording, which is available. So bear with me in a second. So Dave began the talk by, you know, introducing now the motivation to causality with this little picture on the section 1 title screen. So it says, "My lord, we have observed people with umbrellas having more accidents. Order everyone not to carry an umbrella." Well, when it rains, you know, you should have an umbrella because it can protect you, at least if you're a person that doesn't want to get wet. And that's typically the standard case. But now here the person is saying, well, people are having more accidents. Well, and it seems like a cause, right? And so the simple solution is just to say, well, then don't use umbrellas, because getting wet, I guess, is less worse than having accidents. But yeah, as you can see, we have causation already in this little sketch here. So there's a lot to uncover about this topic, and so let's dive deep into it. So here Dave was asking actually the crowd what they think they see on this picture. So if you just look, you see what look like police officers, people, adults essentially, right? Given the KMBC news, we might also think that's in the US. Also, judging by the car, we have two kids. They're all on the street. And yeah, maybe they're playing some kind of game, right? People might play, kids might play something like basketball or something, right? And there were different answers, right? And different perspectives essentially, because people have different priors, yeah. And this is after all a Bayesian kind of formalism in Perl that we are looking at. And yeah, if you think if you think maybe just from the police setting, you might think, oh wow, there's these topics of police brutality and racism and so on going on in the US. So if you're negative minded in that case, you might think, oh, someone is maybe getting arrested, right, or whatever. But then maybe if you're on a positive note, then you're thinking, oh, this is just kids after all, and these police officers are maybe just they're on duty, of course, but they might be just free, right? And they just might feel like hanging out with these kids, so they might just be playing basketball with them. And actually, that's exactly what's happening, right? So we complete the picture now, and we're seeing there's a third officer and another kid, and well, they're just playing basketball with the kids. Here now, Dave asked another question. He asked, "What do you see now here, right? And why do you think people are, wearing umbrellas?" And obviously, the answer would be, well, it must be raining, right? That's why everyone is having umbrellas, right? Even if we don't see it now on this picture. But then again, everyone who has taken maybe a photo knows that, you will not always see the rain, even though it's raining and pouring, actually. An alternative which was said in the audience was maybe, it's a sun shield essentially. But then again, some of these are transparent, so we wouldn't think that. Actually, I don't remember myself what the answer was right now here, but Dave just used this for motivation, so I'll just keep going. And now here's where Dave picked up. So he was just giving this example of saying, yeah, 1 + 1 = 2, very simple. But what if we turn this thing around now? What if we have something like 2 - 1 = 1, right? It's the same identity. And now he's going to tell you more about how this relates to causality. So don't be scared. In 1, 2, 3. And now we're switching to Dave.
So that's why I say causality is hard. If I ask you the question, what's causing the ball to go into the, whatever this is called? Yeah. Right? What do you think? Is it the cat? Is it the shot? Sorry. Yeah. Who all here think that it's the shot? That's why the ball is going into the whatever. We need them at least. Okay, a few people. How many people think it's the cat? Wow. See? We don't need the cat. I'm just saying about the scene. Here you need the cat. Or do you? So that's why I say causality is harder, right? Because here, even people are not agreeing why is the ball, why is this happening, right? Some people say it's because of the shot, some people say it's because of the cat. And maybe if the cat was not there, it would have gone in anyhow, right? Who knows? We'll never know. So causality is harder. That's what we'll see. So sure, some people say cat is the cause. Some people say the shot is the cause. But then if I go into a little bit more philosophical argument, or I go more into a scientific, I delve into the scientific details. Can I just say that the air molecules around the ball and the temperature of the room, blah, 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 it's also causing the ball to go in into the, again, I don't want to say hole, but whatever, right? Yeah. So that's what I want to ask. Why can't we just, if we kind of abstract this argument down and down and down, we can actually maybe even go until the Big Bang and say maybe that's the reason why that's happening. And actually, there are some studies which shows that whatever is happening, you can relate it back if you abstract it enough. You can relate it back to the Big Bang. And there's one very famous quote by Carl Sagan. I think everyone might know him. So if you wish to make an apple pie from scratch, you must first invent the universe. Which is true, right? If the universe wasn't invented, nothing would have happened. So maybe that's the cause of everything happening. So see, even for us humans, causality is not just hard, it's harder. And so you can just imagine what it is like for machines, right? Even with all the knowledge that the machines have, it's very difficult to get this notion of causality. Okay. And now you'll see that causality is maybe everywhere. So these are some different notions that you'll find of causality in different branches of sciences. So classical physics, this is the general theory of relativity. I mean, you can read the sentence, but it just says that what Einstein postulated was that an effect cannot occur from the cause that is not in the back of the event. So basically these light cones, when you see in the theory of relativity, that you can only see what is there in the light cone. So that's what. So this is a more of a paraphrasing of theory of relativity, but that's what, yeah, that's one of the notions maybe. Then in philosophy, where you have the material cause of a being is its physical properties or makeup. So you'll find this term cause everywhere, right? Doesn't matter which branch of science you go. Economics. So 2021 Nobel Prize was won by people who worked on causality. Where they developed these outcome models where the causes of these effects are investigated and whatever. So you'll see that now causality, even like Yuda Pearl, right? The Pearlian notion of causality, which is the most famous one in AI and machine learning. He won the Turing Award in 2014. 11. Yeah. I mean, more also due to causality, but also because of his work in Bayesian networks. So, but you can see that causality is kind of now in the limelight, right? People want to do causality. David Hume. So you'll see that previously it was I'm stressing the fact that causality is omnipresent. But in the next slide, I'm asking the question, is it omnipresent? And David Hume is one of the most famous people who was kind of against causality. He said no, right? So of course, I mean, you can read the statement, but what he says that we as humans, we think of cause and effect, and thoughts are subjective. So basically, you cannot prove causality. And then there's very famous barber's paradox. So it says that there's a village where the barber shaves all those and only those who do not shave themselves. So who shaves the barber? Right? So you can see the paradox here. I'm not going into too much details here, but you can see that there are always these notions where you'll see, although we as humans can think about causality inherently, but then there are always these notions or these paradoxes where you might feel, okay, is causality actually present or not? Okay, so now coming to the more fun part. So now we go into a little bit why machine learning needs causality after all these notions of causality in different branches. So most of the images that I'll show now are from the book of Why from Yuda Pearl, which is a very nice layman introduction to cause and effect. Right? So I think most of you might have heard this, right? So in the late 1960s in the US, there was a lot of debate whether smoking causes cancer or not. And then many of these companies, they put out these advertisements, and they also had these real doctors who they were paying, right, to come and saying that, okay, there's no proof that smoking causes cancer. This is all, yeah. I mean, people still have cancer even if they don't smoke, which is true. But yeah. So the current trend is deep learning, right? Everyone speaks about deeper, deepest models. Now you'll see ChatGPT, these big models that you cannot even imagine coming into picture. So then I asked deep learning model, which is ChatGPT. This is GPT 3.5, I think. So I asked ChatGPT to give me a example causal graph for some unexperienced audience. I just wanted to test the capabilities, right? Is how well it can tell me, or how well it can understand causality, right? So I was kind of surprised. It gave me a causal graph, which I had never seen. It's about sleep and academic performance. And it just said that if you don't sleep well, your academic performance is bad. If you sleep well, it's good. I don't know if it's true or not. It's very general or not. Some people don't sleep much and they still like get good grades, right? But sure, I mean, as I can still accept this fact, right, that this might be true. So this is surprise. I was surprised. And then, of course, I mean, it gave me sleep is it gave me the explanation for that. What is sleep? What is academic performance? Because it's also very important to define these variables, right? And then it gave me a causal relationship. So which was nice, right? So does machine learning already have causal capabilities? I don't know. With this was a very simple example. If you go a little bit complex, maybe not. But sure, I mean, at least machine learning is moving towards that direction, right? It understands, or at least it's kind of seen that in the training data already. So nice. And now then, of course, you'll see, I'm missing some slides here, but we'll see. Okay, then let's skip this. Maybe it's later. Okay. So what are the current challenges in AI, machine learning, data science, whatever name you want to call it? I don't know what is the difference between at least data science and machine learning. People know. Most of these models, especially these deep models, right? So they are black box. You have several models that can predict the probability of someone getting cancer. There you can get probability of someone getting a loan or not. Should someone be given bail or not, right? So you have these models that are actually in practice. So there's a very nice book called Weapons of Math Destruction by Cathy O'Neill. And there she speaks a lot about these kind of models. And she gave these real examples from the United States, where these models are currently in practice and how it's biased towards, or how it's harming basically minorities. So interesting. So that's why we want models in AI to be explainable. We want them to be fair, right? So basically, you should not just, because you have not seen someone in the training data, then you should not bias towards one race, say. So you need a more fairer models. And of course, in 2020, people were still complaining. They were still writing that AI still cannot do cause and effect. Can it still do it today? I mean, we have made a lot of progress, but I think the answer is still no if you talk about, say, a general sense of causality. Yeah. Yeah, so these are the current challenges, as I said, and we have already spoken about it. Deep learning models, they're data hungry. You need millions and millions of examples for them to train. They are mostly black box. They don't generalize very well, right? And of course, they are unfair most of the times. And all of these questions can actually be answered by causality. And there's a lot of work going towards in direction how causality can actually help us answering these sort of questions. And that we'll also see in lectures, like in fairness and explainability, that will come later. We'll see these questions being answered in the lectures. Yeah, so this is the slide. I mean, I skipped that slide, and this is Moritz here, right? So we wanted to test the causal ability. It was, which model was that? This was? Stable diffusion. Yeah. So stable diffusion, a large image generator, right? Which are really good. They can give you very crisp images. So we had this input image, and we gave it a prompt. So there's something funny in the prompt. You might see it, right? So it's called make it a dark starlit night instead of star lit night. And then it gave us this. Not very good, but sure, I can live with it maybe. I mean, there are no stars to be present, but whatever. Right? We didn't say stars. And then Moritz corrected this. And he said, make it a dark starlit. And this is what we got. Right? So this is like the Van Gogh painting, right? Because that's what it has seen in the training data, maybe most of the times. And there are 4 more examples that he has come up with newer examples, but yeah. Yeah, so you can see that still these deep learning models, these large language models, stable diffusion, whatever you want to call these new hype in AI, right? They still do not understand these simple causes and effects. So basically, if I'm asking you to make it a night, for us as humans, it's simple, right? What night means, but what does night entail, or what is the effect of night in a picture, in an image? So AI is still struggling with this. So then let's go in, what is causality? I don't know if there's a single definition for what causality is. But if you go back in time, I mean, we also spoke about the Big Bang, so we cannot go beyond that. But if you go more into philosophical arguments, probably Plato was first to state the principle of causality. Of course, in my opinion, there were people before Plato that spoke about it, but maybe, I mean, this is the one that you can find. Matthew found it. So he writes that everything that becomes or changes must do so owing to some cause, for nothing can come to be without a cause, right? So again, I want to motivate why causality is important, why machine learning for causality is important. So it's not that it is just a new topic, right? It's a niche topic, sure, but people have been talking about causality since ages. And this is William Whewell. I don't know if anyone has heard about him. He was several things. He's British, right? First thing. Second, I mean, he was yeah, philosopher, physicist, chemist, whatever you name it, and he was that, right? And he came up with these axioms of causality. So these three axioms. So first was nothing takes place without a cause. Sure. The magnitude of an effect is proportional to the magnitude of its cause. Maybe the Newton's third law of motion. It's the third one. To every action, there's an equal and opposed reaction, right? So that's the kind of questions that he was asking. If a baseball is moving through the air, it must be moving this way because of some previous interaction with the baseball bat, or someone threw it, right? So it's not that is happening without any cause. So he gave these three axioms of causality. And then he also gave a principle of universal causation, which kind of follows from these axioms of causality, which is, again, in layman terms, it just says that everything happens due to a cause. There's nothing that's happening without a cause. You people are sitting here because of the course, right? Maybe, hopefully. Right? He's sitting here, I don't know why. But okay, so now let's come to Pearlian. As I said, the Turing Award winner, and basically called the father of causality in AI and machine learning. What he says is to build truly intelligent machines, teach them cause and effect. So you have these deep learning models. Are they intelligent or not? That's a different question altogether. But of course, I mean, they have good capabilities, right? So there's no denying that deep learning has changed lives, right? It has changed machine learning, the field as a whole. But if you really want intelligent machine, you really want artificial general intelligence, what people talk about. You want cause and effect. And this statement, which I'm not very sure about, but what he said is all the impressive achievements of deep learning amount to just curve fitting. I don't know if I agree with the statement or not, but sure, I can understand where he's coming from. And then Yoshua Bengio, another Turing Award winner, but for deep learning. He has also said that causality is very important for the next step for progressive machine learning. He's very smart, right? So he won the Turing Award for deep learning. Now he got bored and he said, okay, what's next? Let's go to causality, which is good for the field because now people have started taking more notice of causality within machine learning. But you can see that people are talking about this. And now, this phrase that Mete also spoke about, right? Correlation does not imply causation. Dinosaurs didn't read, now they're extinct, right? Correlation, maybe, right? At least not causation, that's what we can say. But is this statement always true? Are there cases where correlation might imply causation? I mean, because I've shown this Venn diagram here, you know the answer, but I'll show you an example. Previously, I used to have different examples, but now this is my favorite. So this is where correlation does not imply causation, right? So this one shows you the Brexit, right? These people said majority remain. This people said majority leave. These were the areas. And this is in 1992, the mad cow disease that happened in Britain, where they said remain, there was not, it was free, no mad cow disease. Where they said leave, they had. So I'm not asking you to jump to conclusions, but you can see where I'm going with this, right? Classic case of correlation. Is it causation? I don't know. Again, I don't know, right? Maybe, maybe not. Most probably not, right? Okay, so this is where you can quite confidently say that correlation does not imply causation. So they are different things. But now this, and I want one of you to answer why I feel this is correlation and causation. Correlation implies causation, but why a third factor? The confounder, the common cause that Mateo also spoke about, right? A little bit. So this graph shows global warming, the trend of global warming from 1800 to 2000. And this shows the level of piracy, not like what you do in the laptop and download illegal stuff, but real piracy, right? It's Pirates of the Caribbean, if you remember, right? So you can see a very nice correlation. As the global warming went up, the piracy went down. Can someone tell me why is that maybe a causation? Yeah.
Because global warming is due to the industrialization,
Mhm.
which caused the pirates to go out of business.
Okay. Yeah, there's still pirates in Somalia for sure. But maybe he's right. But I also have something else in mind. Yeah. Anyone else? It's simple. Come on, I think. Yeah.
The price of global warming, you see, won't be very.
But they're still there for now. But you can see that, which I agree with, they won't be here much like after maybe 200-300 years, who knows. Okay. Well, why I feel maybe industrialization, he's right? So there's no right answer to this, right? What I feel is that because of global warming, the seas have become more turbulent, right? There are more like storms and everything. And maybe that's one of the factors why piracy has gone down. But industrialization, right? Maybe seas going dry. Yeah.
Or maybe with the time, there were more airplanes flying around.
Yeah.
And due to that, global warming is more, and because the ships are not driving so much.
Mhm. Yeah. Yeah.
So
So maybe people flying more, or maybe what I said, that seas are more turbulent. Now, no, I'm not saying I'm right. I'm just saying that's also one maybe, right? So we just got these 4 factors, right? So we got the 4 factors for the third factor. So this is correlation implying causation, but maybe via a third factor, right? Because of this, piracy is going down due to global warming, right? So you have this, so you got so many third factors already. So interesting, right? Hopefully, till now. So then I asked ChatGPT also, right? Because everyone, even no one knows about AI, machine learning, they know about ChatGPT, right? So I asked, what is the effect of global warming on pirate ships? I wanted to know. Does it think what the way I think, or anyone here thinks, right? So no direct scientific evidence or research that has been done that does effect of global warming on pirate ships. But see, we can separate on some potential indirect effects, rising sea levels. See, smart. Changes in weather patterns, ocean acidification, temperature changes, economic and geopolitical effect, correct? So everyone here was correct, right? So wow, I mean, ChatGPT, I was so surprised. It has solved AI. Let's just go home, right? Yeah, but impressive. So again, I don't want to claim that deep learning has these, or ChatGPT has causal capabilities, but at least it's moving into the correct direction, right? So you have at least this training data where you can have some notion of cause and effect. So which was nice. So that's why you see why causality is important, why it is becoming important. Any questions till now? No? Good. No one has, yeah.
Before you said that causality is a niche topic, right?
Yeah.
But it seems to me like, isn't there at some point in the future going to be that all systems have to use causality in order to keep up?
And that's the hope. Yes.
That's why we are doing this.
Exactly. No, I completely agree, right? I mean, so there's this, I haven't put it here. I saw it just a few days back on Twitter. There's this, there's a curve of AI research. I'm forgetting the curve. I don't know what it's called. And it basically shows,
Right, like the cycles, I guess.
Yeah, there's these cycles, and then they put these AI topics on this curve, right? Where the AI topics are. Is it hype? Yeah, are people working on it? And after how many years will the topic become dormant, right? And so causality was still in the bottom, right? So it's still growing. But I think for sure that's the aim. I mean, if machines can have a real notion of cause and effect, they can generalize without looking at examples, right? For us as humans, it's easy to generalize. If machines can do it, then yeah, I mean, and that's the hope that if you, as I said, as Yuda Pearl, as I showed you the slide, Yuda Pearl said that in order to get these real intelligent machines, you want cause and effect. So you want machines to have cause and effect. So yes. Okay. Little bit. Yeah. A principle that I want to show. Again, this is based or related to the confounding that we were talking about. Right. So this is Reichenbach's common cause principle, where he defined confounders. The principle just says that if two random variables are statistically dependent, then there exists a third variable. There has to be a third variable that causally influences both. So this is again the common factor we were talking about. I think it's a very restrictive assumption, maybe, but sure. I think that's the common cause principle. And now let's come to the fun part, right? So whenever you read any causal textbook or you take any causal class, you see videos, people want to show that correlation does not imply causation. So now maybe let's just forget about the third, the confounders here, but this is a very classic paradox that they show. So this is called Simpson's paradox, right? So you see here, so there's a disease. There are 3 stages: mild, severe, 2 stages, mild and severe. And there are 2 treatments, A and B, for that, right? So maybe it's COVID, mild and severe, and there are 2 treatments for COVID, A and B. If I just look at, suppose we don't look at this column, right? The total one. If you just look at the first 2 columns, you'll see that 15% of the people who took the treatment A got well, 30% of the people who took the treatment in the second case, I mean, they got well, right? And for treatment B, it was 10 and 20%. So if I ask you, if I just show you this table, and I don't show you the last column, I ask you which treatment is better. Right? Of course, you'll say treatment A because more number of people are getting cured. Now I unmask this and I say, look at that, the final one. It's 16% treatment A, 19% treatment B. Can you see the paradox there? Right? So even though more percentage of people are getting better here, when you like abstract down to the categories, in the total, they're less. And in B, it's like, okay, it's less number of people, but overall it's more. So without causation, how will a machine learning system actually define this or predict this? It's impossible, right? Because it'll just break here. Because I mean, this doesn't make sense at all. But then of course, if you have some sort of causal structure, right? So you can just say, okay, I can look at the number of people who are getting the treatment. They are very large in A, there are less people in B. And you'll see most of the people who have mild diseases, they're generally more, they'll get better. I mean, the chances of them getting better is more rather than people who have severe disease. And you can see that many people mild here, they're just giving treatment A when it's mild, right? So looking at this causal structure, then you'll be able to describe this problem. So these are the 2 scenarios in which you can answer Simpson's paradox. So the first one is where treatment A is preferable, right? So this is the time. Oh man. This is the time, right? When you're going for the treatment, this is some confounder, and this is the condition, I mean, and this is the treatment, right? No. So this is the treatment, this is the outcome, and this is some sort of a confounder. And you can say that when you have a mild condition, then you prefer treatment A. But in treatment 2, you can always, if you know the causal structure, if you say that suppose treatment A is very difficult to get because many people are getting it, right? 1,400 people who got that treatment. So you have to stay in line. And when you stay in a queue in a line, or after a few days, your situation maybe deteriorates. You go to more severe condition. If you go into a severe condition, chances of survival become less. So here you can see that the time is kind of affecting your treatment as well, right? here. It's affecting the confounder that I spoke about, which is the time, the treatment. So here treatment B is preferable because then you are going to more severe cases. So without the notion of cause and effects, it's kind of impossible to answer this question. Okay. So even within causality, within AI machine learning, there are several models. It's not just Pearlian notion of causality, right? So there's also Nyman-Rubin, right? So they call their theory potential outcome theory. So these randomized control trials, if you have heard about them, these are mostly potential outcomes, right? And I don't know if we are covering potential outcomes here. So
we'll have a
little, right?
So we go beyond. So for example,
Okay.
when we talk about actual causation range.
Yeah, correct, right? So you'll see how you move from potential outcome theory to like Bayesian networks and DAGs. So basically getting these classical AI concepts in causality, or causality into these classical AI concepts. Okay, so everything is hunky-dory till now. We all agree that we need causality, machines need causality, everyone needs causality, right? But there's a problem of causality or causal inference. So this is Amy, and Amy is depressed, right? At time t-1. I hope there's no Amy here. Otherwise, you change the name. So Amy is depressed, and at time t-1, Amy adopts a dog. And at time t, we see that Amy is happy, right? So then what is the cause of Amy getting happy at time t? Is it because she adopts a dog? Or if she hadn't adopted a dog, she would have been happy anyway, right? So can you see what is the apparent problem here? Here. Yeah.
You have no control. You don't know if the ceasing of the depression syndromes are just because of the treatment for the dog or both.
Mm-hmm. Exactly. Right? You had some other answer?
Yeah, I want to say the same.
Yeah. Yeah, exactly, right? So you can only observe one of them, right? So right now we have observed that Amy has already adopted a dog, and we have observed that she's not depressed anymore. But to answer the proper question, we also need to have this where she did not adopt a dog and she was still happy, but that cannot happen. Unless you invent a time machine, you cannot do that, right? So this is called the fundamental problem of causal inference. Because again, it's impossible to observe both of these cases. So how do you even affect the cause, measure the cause and the effect? Okay. So this is a way to represent. So you'll see this directed acyclic graphs a lot, right? So this is a way of representing causal graphs. And I mean, this is, I don't want to go into much. These are just Markovian blanket. So it just says that if I want to know about this variable, then I just worry about its imaged parents, right? But again, I mean, so it's about randomized control trials. Why are these important? Because then you have this control group, as you were saying, and then you can now observe both of them. So this is one way to kind of remove or solve this fundamental problem of causation. And Pearl's causality, which we'll look in this lecture throughout. This is the formalization which has the most success in AI and machine learning. There have been lots of work within AI/ML, but also in cognitive science, right? Which kind of tests this theory. And this is kind of the cat example I showed you, right? If there's a ball that is going here, and if it collides with another ball, does it make it to go in, or if it wouldn't have collided, it would have gone in anyhow? So all these kind of questions that we'll see, that we'll learn about, why causality is important. So what are the advantages when you have some sort of causal structure with you? When you learn the causal structure, you assume a causal structure. That we can talk about these modeling assumptions, right? So now we know the inherent process due to which the data was generated, and then the problem becomes easier for you, right? So for example, if you've taken statistical machine learning, if you don't know the underlying data distribution, how does a model even fit it, right? You assume your data distribution. So Yeah, so the difference between causality and then this statistical machine learning or this probabilistic graphical models. In probabilistic graphical models, you talk about conditional probabilities, but in causal AI models, you talk about these causes and effect, although you can use the same representation to represent them, right? The DAGs, but the answer that you're searching for becomes different. Final section, what does Pearlian causality looks like? So first of all, so this is a image from a book by Jonas Peters, which was kind of the first book that went towards this intersection of causality and machine learning. And you see here that a causal model is strictly more general than a simple probabilistic model. Because a probabilistic model, you can just have these conditions, these observations and outcomes. But causal models, you can have this plus changes, interventions, right? So what these things are, we'll see now quickly. The causal hierarchy that Mete will talk about in detail next week. So this is just a quick overview. Pearl presented this a ladder of causality, right? So the first is association, your classical machine learning models or your random forests, decision trees, MLPs, blah, blah, blah. So they all lie here in association, right? Because they don't have any notion of causality. They just have this correlation-based learning. Then there's intervention. So intervention is when you do something, right? So for example, you came to the class and sat. So that's an intervention, right? So and the effect is that now you're listening to my voice. I'm sorry for that, but. So if you see some examples, right? In association, you have this, what does a symptom tell me about a disease? But in intervention, if I take aspirin, so I've taken an action, will my headache be cured? You can answer these set of questions, right? And the last rung, which is the most difficult rung, is counterfactuals. It's about imagining. It is these thought experiments maybe that Einstein did, right? So you can answer questions like, was it the aspirin that stopped my headache? And if I wouldn't have taken aspirin, what would have happened, right? Those kind of questions. You have to go into this rung of causality to answer these. And there's not much work, so it's kind of an open question. Only Florian has one model. So this is the first rung, right? Simple. It's elementary, my dear Holmes. Simple associations. If you've seen Sherlock Holmes, that's what he used to do, right? I don't know if he used to do causation or association, but yeah, he used to associate what has happened with what might have happened before. So this is simple association, which is the first level of Pearl's causal ladder. Why is it not coming? Okay. This is the intervention, right? This and you're gone. So doing something, what is the effect of that?
There's the copyright on this one.
Who cares? So I'm leaving it. This is a classical example, my example of intervention. You do things and you observe what that thing led to. And okay, so this is, let's not worry about it. And this is like the counterfactuals, right? Where he says, this is, and sorry, I could not travel both and be one traveler along I stood. So we have to choose between one of them, the paths. You can only choose one, right? So a good counterfactual will be that you might be thinking right now, what the hell, I would have sat somewhere and eating something or maybe enjoying, why am I sitting here, right? But you'll never know what would have happened. So counterfactuals, imagining, right? So we spoke about that. Yeah, same thing. So this is an important slide. So we'll see where these different machine learning models lie on this Pearl's causal hierarchy. So as I said, associations, where you just look at correlations or associations. Then you have these decision trees, deep networks, machine learning in general, right? Second is a more specialized interventional. We have some work there, but if you look at this more general machine learning frameworks, then you can talk about reinforcement learning, causal Bayesian networks, or POM-DPs, if you've heard about them. You can talk about interventions in those sense. Counterfactuals, you don't have classical machine learning. They didn't have any notion of how to even handle counterfactuals. So you need a new representation for that, right? And that's what are called structural causal models. So quickly, what are structural causal models? I just think of them as this data generating process, right? So I have some sort of an underlying causal graph, and I can represent that graph as so it's a causal model for me. It has some sort of a structure, and it's a structural causal model. But more formally, it's defined as this. It's a tuple where V are, so you have V, U, F, and PU. V are endogenous variables. Endogenous means the variables that you observe in the world, right? Exogenous variables that you don't observe, maybe some noise that you don't know that it exists or not. Then you have some functions. So basically you have the parents of I, and then you have some exogenous variables. And if you put these, what will be the outcome? What will be V? What's the value of V? These are these functions that determine that. And then your PU is the probability distribution of your exogenous variables, because of course you don't know about, you haven't observed these, but you need to assume some sort of a distribution for these exogenous variables. And an assumption which has now been, I think there has been work that it has been relaxed. So as I said, there should be no cycles. That's why you have directed acyclic graphs. But now there's also work on cyclic graphs and how causality can be handled in those cyclic graphs. So the way, if you have given a causal graph, how can you represent it as an SCM or vice versa, right? So X causes Y, or drug causes a disease to be better. Then you can represent it like X is dependent on nothing. You can see there's nothing here. Y is dependent on X and other noise variables. So you see a arrow going from X to Y. And then Z is also, it's not, you don't see any arrow coming in. And these arrows, I mean, so you don't know the real causal relation here. So it's just these double arrows. So given these structural causal models, you can generate data, and then you can use them in your favorite machine learning models to basically get something out, right? So that's the whole idea. These are the three basic graphs, which are also called gifts from the gods. Someone said it, I don't know, it's Pearl or who. But these graphs are what you'll see in causality the most. So this is a simple chain, X causes Y. This is called a fork. So you have like a common cause for these two variables. And this is a collider. So basically your two variables that collides on this variable. And this is a special case, right? And you'll understand why in later classes. Yeah, let's maybe skip this because it's just, yeah, again, what's the difference between observation and intervention? You can see here that observation, you have this structural causal model. And if I just say I want to put X to X, you just do that here. You remove any function or anything, right? So that's just sort of interventions. Not important now. The difference between causality and conditional probability. So suppose you fall from or not you, someone falls from a tall building, and that causes most probably death, right? But then we can say that death is possible even without fall. So when you have these conditional probability arguments, then you cannot answer these kind of questions. Because I can say that suppose all the people who fall get wings and it ensures survival. In these cases, you can just ask these conditional arguments, but you cannot answer causality. So that's what it says. So again, association versus causation. I think I bored you enough about this. So yeah, so major topics that we'll be seeing in the course. So this is, suppose you are given some data and you want to find out the inherent causal relationship between variables in the data, right? So that's called causal discovery. You want to discover causal relationships between different variables. So that's one. Another one is, I think, causal representation learning. At least there's one lecture. Right now, I think most of the people you see, most of research in causality, they are doing causal representation learning, right? Because then you can use deep neural networks more principally. And then you want to find out the causes and effects, right? So the causal effect. Yeah. Same thing. And quickly, just 2 or 3 more slides. I want to tell you some of mostly biased towards our work, how machine learning has been used for causality, right? We spoke about interventions, right? Where you do something and then you want to estimate the effect. You want to estimate the distribution of your interventions. So basically, this is work that Mete's work in NeurIPS in 2021. So where we use something which are called sum product networks. These are probabilistic models, generative models where you can predict densities, right? So we did that. This is Florian's work. So we actually took sum product networks to the other rung. I'm telling you, as I said, that handling counterfactuals is the most difficult part, right? Because of course you need to invent a time machine. But if you make some assumptions, then you can also handle counterfactuals. Man, why is it happening like this? It's so sad. It's too quick to see anything, but so let me move. And then it had to be slow. I don't know what's fast.
It was fast, but I think it was
Okay.
Yeah.
But yeah, so and then you see, so now you'll see that you have all heard about explainable AI. AI is black box. We want explainable models. But now there's been this growing noise that the real explanations are actually causal in nature, right? So you'll also see a lecture here. Moritz will, I think, give it, right? On explanations. Oh, fairness. I don't know. Maybe you will give it. So yeah. So how you can leverage causality for developing these explainable AI models. Right. So we have some work on this as well. And these are some of the references. So there are 2 books. So this is the Bible of causality, right? So this is not only AI related, but it's just general causality by Yuda Pearl. This is Elements of Causal Inference, which is more towards machine learning and causality. And then there are these 3 lectures that you can look, right? For me, I like his lecture the most. Even although he speaks about more towards the potential outcomes, right? But still, I mean, I think they're more enjoyable. This is more classical causality by Eunice Peters and Elias from New York, Columbia University. These are like, I think there's 1 hour and this is also 4 hours lectures. There's a complete course, but this is, I think, better than other 2, in my opinion, at least. So after all this, right, 1.5 hours, whatever. So what we have come across, what Yuda says, I removed what Mete says, but what Yuda says, as X-rays are to a surgeon, graphs are for causation, right? So we want to study about causality in machine learning and AI, and you will understand, you'll see, even though in the next lecture it's about probability and other things, but you'll see how graphs are actually central in incorporating causality in machine learning. So that's it. If there are any questions you can ask right now, or as Mete said, you can go to Mattermost and you can ask there. Thank you. Any questions? Yeah.
Yeah, so I wanted to ask about the difference between interventions and counterfactuals.
Yeah.
So which of them are used more, or do we do both at the same time?
So within machine learning, or?
Yeah.
So as I said, like there's not much work on counterfactual methods for machine learning. There are very few works. One is by Elias's group and one is from Florian here. So I don't think so there's much work. So people are still kind of on the second rung of causality. Because for counterfactual machine learning, as I said, you need to make a lot of assumptions, right? Because you don't even have the counterfactual data. Because what you don't observe, how will you even predict that? Right? Because counterfactuals means that it's imagining. You are imagining something that has not happened. So you're not observed it. So you don't have any data for that. But if you say that, okay, there is some data available, then you can sure go into that. But a more principled approaches for counterfactuals, they don't exist. Interventions still, because you're doing some intervention, you're getting some effect, right? So you can still estimate those things. So yeah, mostly it's interventions. Yeah.
Potential graph into a causality graph.
I don't think so. If you have some sort of confounders, maybe as I showed you, right? But if you have a classical coefficient, how do you even represent it? It's just a matrix, right? Turning that into a causation, I don't see it unless again you have these assumptions of confounders and other things. I don't know if you can directly do that. Yeah. Anything else? Okay, then see you next week. Thanks.